Imagine boarding a rocket ship, the most powerful engine, the most advanced technology. In the depths of space, no friction, no air resistance. You press the accelerator. You accelerate. Faster, even faster. 1,000 kilometers per second. 10,000. 100,000. And you're still accelerating. Because in space, there's nothing to stop you. In theory, you could accelerate forever, right? But here's the truth. You won't. As you approach the speed of light, something changes. Your engines continue to produce the same power, but your speed increases less, and less. Eventually, no matter how much energy you expend, you will never reach the speed of light. Why? Because the universe won't let you. The speed of light isn't a limit, it's a prohibition. One of the most fundamental, unchangeable rules of the laws of physics. And throughout this video, we'll discover why. The shocking truths behind Einstein's theory of relativity, the nature of space and time, and E equals mc squared. Because the speed of light limit isn't just a technical obstacle, it's a fundamental consequence of how the universe works. Are you ready? Because this will go completely against your intuitions. Let's begin now. First, let's understand how fast the speed of light is. Approximately 300,000 kilometers per second. More precisely, 299,792.458 kilometers. Scientists denote this with the letter c, and this is an incredible speed. For perspective, light can circle the Earth 7.5 times in 1 second. It can travel from Earth to the Moon and back in 1 second. It takes 8 minutes and 19 seconds to reach Earth from the Sun. Light from Proxima Centauri, the nearest star, travels for 4.2 years. Incredibly fast, right? But here's the interesting part. The speed of light isn't just very fast. It's special, because the speed of light is the maximum speed in the universe. Nothing, no particle, no signal, no information can move faster than light. But why? Why does the universe have a speed limit? And why is this limit exactly 300,000 kilometers per second? The answer lies with Einstein, and it begins with a strange problem at the end of the 19th century. In the 19th century, physicists made incredible progress in electromagnetism. James Clerk Maxwell developed the unified theory of electricity and magnetism. These equations, known as Maxwell's equations, explained how electric and magnetic fields work. And these equations revealed something astonishing. Light is an electromagnetic wave. Vibrations of electric and magnetic fields propagating through space. And Maxwell's equations calculated the speed of light exactly, 300,000 kilometers per second. But here's the strange part. Maxwell's equations said that the speed of light was constant, even if the light source was moving. Even if you were moving. Light always travels at the same speed. This was absurd according to 19th century physics, because in your daily experience, speeds add up. Galilean relativity tells you this. If you're walking on a train and the train is going 100 kilometers per hour, your speed relative to the ground is the train's speed plus your walking speed. If you throw a stone from a car, the stone's speed is the car's speed plus the throwing speed. This makes sense. It's intuitive. It's what you observe every day, but not for light. Maxwell's equations say light is always at speed c, no matter what you do. Are you running toward the light source? Light is still c. Are you running away from the light source? Light is still c. Physicists were confused. Perhaps, they said, light propagated through an invisible medium called ether, just as sound propagates through air. And perhaps Maxwell's equations gave the speed relative to the ether, just as the speed of sound is relative to air molecules. This seemed reasonable. So if Earth was moving through the ether, the speed of light measured in different directions should be different. Just as sound reaches you at different speeds when you run against the wind versus with the wind. But then, in 1887, Albert Michelson and Edward Morley performed their famous experiment. Using a very precise interferometer, they measured the speed of light in different directions. If ether existed, a difference should have been detected. But they found nothing. Light was exactly the same speed in all directions. There was no ether, or at least no experiment could detect it. And this plunged physics into a deep crisis. Maxwell's equations clearly seemed correct. They explained electromagnetism perfectly. But the constant speed of light didn't match Galilean relativity. Something was wrong. But what? Physicists tried to solve this problem for years. Lawrence and Fitzgerald proposed that objects moving through the ether could contract. This could explain the Michelson-Morley result. But this was a patch, not a deep understanding. Then Einstein came. Albert Einstein was 26 years old, a young clerk working in a patent office in Bern, Switzerland. Brilliant in physics but unknown in the academic world. And in 1905, he published a paper titled Zur Elektrodynamik bewegter Körper, on the electrodynamics of moving bodies. This paper changed physics forever. Einstein said the problem wasn't the ether. The problem was our fundamental assumptions about time and space. Since Newton, for more than 200 years, physicists had assumed that time was absolute, a universal clock, running at the same rate everywhere, and that space was also absolute, a fixed stage on which events occurred. Einstein said, no, time is not absolute. Space is not absolute. Both are relative, dependent on your motion. Einstein started with two simple postulates. First, the laws of physics are the same in all inertial reference frames. That is, for everyone moving at constant velocity, the laws of physics are the same. Even if you're on a train, even if you're in a rocket, physics experiments yield the same results. Second, the speed of light in a vacuum is the same for every observer. The motion of the source or the motion of the observer doesn't matter. Light is always at speed c. From these two simple assumptions, just these, Einstein derived incredible consequences. Mathematically, logically, inevitably. First, time is relative. If you're moving close to the speed of light, your time slows down. Really, this isn't an illusion. It's not a matter of perception. Physically, seconds for you can be hours or years for someone outside. This is called time dilation, and it has a formula. Delta t equals gamma times delta t0, where delta t0 is the time in the moving frame. Delta t is the time in the stationary frame. And gamma is the Lorentz factor, 1 divided by the square root of 1 minus v squared divided by c squared. If your speed is close to 0, gamma is 1. Time runs normally. But as your speed approaches the speed of light, gamma grows. At 50% the speed of light, gamma is approximately 1.15. At 99%, gamma is approximately 7. So while 1 hour passes in the moving frame, 7 hours pass outside. And at the speed of light, gamma is infinite. Time stops. This seems like a crazy idea, but it's real, and it's observed every day. GPS satellites orbit above Earth at 4 kilometers per second. Not very fast, only 1,000th of 1% of the speed of light, but fast enough that time dilation is measurable. Clocks in GPS satellites run approximately 7 microseconds slower per day compared to clocks on Earth. 7 microseconds. Very small, right? But GPS calculates your position with nanosecond precision. If time dilation weren't taken into account, your GPS would be off by several kilometers every day. So every GPS app on your phone confirms Einstein's relativity. Every day. Billions of times. Second, length is relative. If an object is moving close to the speed of light, it contracts in the direction of motion. Really, physically. If a rocket is traveling at 99% the speed of light, that rocket, for someone watching from outside, appears only 14% of its original length in the direction of motion. This is called length contraction, and the formula is L equals L0 divided by gamma, where L0 is the original length, L is the observed length of the moving object. Again, this is real. In particle accelerators, protons are accelerated to speeds very close to the speed of light. And these protons, in the laboratory frame, appear incredibly flat, like a UFO. Third, simultaneity is relative. Two events, occurring at the same time in different places, can be simultaneous for one observer, but not for another. The concept of now is not universal. It depends on your motion. This is the strangest consequence, because in everyday life, now seems absolute. But it's not. If you and a friend are moving at different speeds, you can't agree on what now is. Example, imagine two space stations, one near Earth, the other near Mars. For you, an event at the Earth station and an event at the Mars station can occur at the same time. But for a rocket moving close to the speed of light, the Earth event occurs first, the Mars event later, or vice versa. This is shocking, but mathematically inevitable and experimentally confirmed. And fourth, most important for our topic, mass and energy are related. E equals mc squared, the most famous equation in history. And most people don't know what it means. This equation says, mass is concentrated energy. Every kilogram of mass equals 90 quadrillion joules of energy. 1 gram of mass equals the energy of the Hiroshima bomb. But it has a deeper meaning. Because in relativity, an object's total energy isn't just rest mass energy. Kinetic energy is included too. The full equation, E equals gamma times m times c squared, where gamma is again the Lorentz factor. If your speed is 0, gamma is 1, and E equals mc squared. Just rest mass energy. But if you move, gamma increases, and your total energy increases. You're not just adding kinetic energy, your effective mass is increasing. Now, to understand the speed of light limit, let's think about acceleration. In Newtonian physics, accelerating an object is simple. You apply force. F equals m times a. Force equals mass times acceleration. The more force, the more acceleration. In theory, you could reach unlimited speed. But in relativity, things are different. In relativity, when you apply force, the object's speed doesn't increase. Its energy increases. And as energy increases, effective mass increases. And as mass increases, the same force produces less acceleration. Mathematically, F equals gamma cubed times m times a. Gamma cubed. So as speed increases, it becomes 3 times harder to apply the same force. As you approach the speed of light, gamma goes to infinity, and infinite force is required to produce the same acceleration. What does this mean practically? It means You start accelerating a rocket. At first it's easy. Your speed reaches 1,000 kilometers per second, 10,000, 100,000. Nice. But when you reach 10% the speed of light, things start to slow down. Your engines are producing the same power, but your speed is increasing more slowly, because as your energy increases, your effective mass is increasing. At 20% the speed of light, even slower. At 50%, very slow. At 99%, almost stopped. A concrete example. Let's take a 1 kilogram rocket. To accelerate it to 10%, the speed of light requires approximately 400 trillion joules. A lot, but possible. To get to 20%, not 4 times, approximately 5 times. To get to 50%, approximately 15 times. To get to 99.999999999%, c minus 1 meter per second, approximately 20 quadrillion joules. And to reach exactly the speed of light, infinite energy. Mathematically, impossible. That's why you can't do it. To reach the speed of light requires infinite energy. And there isn't infinite energy in the universe. Even the total energy of all the stars in the entire galaxy isn't enough. This isn't an engineering problem. A better engine, better fuel, more efficient design, nothing helps. Because the problem is in the laws of physics themselves. The speed of light is an unreachable limit. But wait, you might say, photons, light particles, are moving at the speed of light. How do they do it? An excellent question. And the answer is surprisingly simple. Photons have no mass. In the equation E equals gamma times m times c squared, if m is 0, what happens? Normally, E should also be 0. But gamma can also be infinite. Infinity times 0 is indeterminate, so a non-zero energy is possible. But only if the speed is exactly c. So massless particles, photons, gluons, perhaps gravitons, always necessarily move at the speed of light. They can't go slower. They can't stop. They can't go faster either. Everything with mass, electrons, protons, neutrons, atoms, molecules, rocks, rockets, planets, stars, you, can never reach the speed of light, can only approach it, even with infinite energy. And this leads us to a very deep question. Why is the speed of light this value? Why exactly 299,792.458 kilometers per second? Why not faster? Why not slower? The honest, scientific answer, we don't know. The speed of light is one of the fundamental constants of the universe. Just like the gravitational constant g, Planck's constant h, the charge of the electron e, the fine structure constant alpha. These are numbers that appear in physics equations. We measure them, we use them, but we don't know why they have these values. Perhaps there's a deeper theory, perhaps string theory, perhaps M theory, perhaps loop quantum gravity. Perhaps this theory derives the constants. Perhaps the geometry of 11-dimensional space determines the speed of light. But right now, we just measure and accept. These are the laws of physics. The universe is this way. But here's a deep insight. The speed of light isn't actually about light. The speed of light is really the speed of causality. The maximum propagation speed of cause and effect. The maximum speed of information in the universe. To understand this, let's think about causality. In everyday life, cause comes before effect. You trigger an event, you press a button, and the result occurs. A light turns on. Makes sense. But if information could travel faster than light, causality could be broken. Here's an example. Suppose you could send a signal faster than light, 600,000 kilometers per second, twice c. Now remember special relativity. Simultaneity is relative. Observers moving at different speeds see the order of events differently. So if you send a faster-than-light message from one space station to another, for the first station, the message goes to the future. But for the second station, moving at a different speed, the message goes to the past. And if the second station sends a reply, again faster than light, this reply could arrive in the past of the first station, before you sent the message. This is a paradox. You're sending yourself a message in the past. You send a message saying, "I won't send the lottery numbers tomorrow." But then you forget to send it. But you already received it in the past. So did you send it or not? Nonsensical. That's why the universe doesn't allow it. The speed of light isn't just the speed of photons, it's the speed of causality. And to preserve causality, information can't go faster than light. Now, let me ask you a different question. Have we ever seen anything going faster than light? The definite answer, no, never. Every particle accelerator experiment, the Large Hadron Collider at CERN, the Tevatron at Fermilab, the Linear Accelerator at SLAC, accelerates particles to incredible speeds. At the LHC, protons reach 99.9999978% the speed of light. Incredibly close, but only 3 meters per second below the speed of light. And when scientists add more energy to them, the protons don't go faster. They get heavier. Their effective mass increases, exactly as Einstein predicted. Cosmic rays, high-energy particles from space, have much higher energies than the LHC. Some have 1 trillion electron volts. Some have 1,000,000 trillion electron volts of energy. But even they don't exceed the speed of light. They just move incredibly close to the speed of light. 99.999999999%. But not 100%. Never 100%. Every observation, every experiment, every measurement, all confirm Einstein. The speed of light limit is real, unbreakable, certain. But some people ask, what about tachyons? Faster than light particles. Tachyons are completely theoretical particles. No experiment has observed them. But some physicists like to think about how they would behave if they existed. According to theory, tachyons would always move faster than light. They could never slow down. Just as normal particles can't exceed the speed of light, tachyons can't go below the speed of light. And they would have strange properties. For example, tachyons would speed up as they lose energy. They would slow down as they gain energy. Backwards. And the strangest part, tachyons, in some reference frames, would appear to be going backwards in time, moving toward the past, not the future. This completely breaks causality. With tachyon messages, you could send information to the past. You could create paradoxes. Most physicists therefore believe tachyons don't exist, because if causality is broken, the laws of physics become meaningless, and the universe seems to have meaningful laws. So tachyons are probably, almost certainly, just a mathematical curiosity, not real. Now another question. What about the expansion of space? The universe is expanding. Edwin Hubble discovered this in 1929. Distant galaxies are moving away from us, and the farther they are, the faster they're moving away. Hubble's law. V equals h times d. Velocity equals Hubble constant times distance. Now, think about very distant galaxies. 10 billion light-years away. According to Hubble's law, these are moving away from us faster than the speed of light. How? Doesn't this violate the speed of light limit? No, because these galaxies aren't moving through space. Space itself is expanding, and there's no speed limit on space expansion. Einstein's relativity says nothing can move through space faster than light. But there's no constraint on how fast space itself can expand. Analogy: draw dots on a balloon. Inflate the balloon. The dots move away from each other, but the dots aren't moving on the balloon's surface. The surface is expanding. The same thing applies to the universe. Galaxies aren't moving through space. Space is expanding and carrying them along. Strange but true, and perfectly consistent with observations. What about wormholes? The shortcuts you see in science fiction movies. Einstein's general theory of relativity, the theory of gravity, theoretically allows wormholes, tunnels in spacetime connecting two distant points. If a wormhole existed and you could pass through it, you could go from one point to another instantly, or nearly instantly, without traveling faster than light, just using a shorter path. Just as when you fold a piece of paper, the two edges of the paper come closer. Instead of walking on the paper, you could jump directly. But there are big problems. First, to keep a wormhole open requires exotic matter, matter with negative energy density, and we don't know if such a thing exists. Second, natural wormholes probably don't exist. They might have formed during the formation of the universe, but would be extremely rare and extremely small. At the Planck scale, trillions of times smaller than an atomic nucleus. Third, to make an artificial wormhole, you'd need to bend spacetime incredibly. This requires energies on the scale of planetary mass, perhaps more. And fourth, wormholes are probably unstable. When you try to open them, they collapse instantly. They attract mass and destroy themselves. So in practice, wormholes are probably not useful. Not a realistic method for faster-than-light travel. So what's left? Can the speed of light limit really not be broken? According to our current understanding, yes, it can't be broken. Because this isn't just a technology problem. Better engines, better fuel, smarter design, these don't help. The problem is in the structure of the universe. Einstein's relativity has been tested for more than a century. Thousands of experiments, millions of observations. Each one confirms relativity. No exceptions. GPS satellites, particle accelerators, cosmic rays, nuclear reactions, gravitational waves, black holes, all behave exactly as relativity predicts. So the speed of light limit seems certain. But this doesn't mean hopelessness, because travel close to the speed of light is still possible, in theory. 99%, 99.9%, even 99.9999%. These are achievable. Just require enormous energy. Antimatter rockets, fusion engines, light sails, perhaps other technologies, and time dilation helps. Because for the astronaut in the rocket, the journey takes much less time. To Proxima Centauri, 4.2 light-years away. Traveling at 99%, the speed of light takes 4 years for Earth. But for the astronaut in the rocket, only 6 months. To the center of the galaxy, 26,000 light-years away. Traveling at 99.9999999%, the speed of light takes 26,000 years for Earth. But for the astronaut, only 20 years. So in theory, you could cross the galaxy in a human lifetime. according to your time. But for the people on Earth, thousands of years will have passed. When you return, everyone you knew will be dead. Civilization will have changed, perhaps even disappeared. This is the tragedy of interstellar travel. Time dilation saves you. But does it make your journey meaningful? I don't know. Perhaps in the future, humanity will build generation ships, massive spaceships traveling for centuries or millennia, generations living, reproducing, dying inside, or perhaps sleep technology, astronauts in deep sleep, centuries passing, or perhaps consciousness uploading, digital brains traveling as information at the speed of light. Who knows? The future is uncertain, but one thing is certain. We can't exceed the speed of light. The universe won't allow it. And maybe that's good. Maybe that's what makes the universe interesting. Because if everything were instantly accessible, there would be nothing left worth exploring. The speed of light limit keeps the universe vast, mysterious, worth exploring. So we can view the speed of light limit not as a restriction, but as an invitation. The universe is saying, there's a lot here, but you can't access it easily. You need to work. You need to think. You need to be creative. And maybe that's the most beautiful truth, because you, in this vast universe, are a small being on a small planet, made from stardust, held together by quantum fields. But you think, you explore, you understand. Einstein, sitting in a patent office using only thought experiments, discovered one of the deepest secrets of the universe. The speed of light isn't just a speed. It's a fundamental part of the fabric of space and time, a fundamental protection of causality, a fundamental feature of the structure of the universe. And you now know this. You can't go faster than the speed of light. But understanding this gives you the power to understand the universe, the power to understand physics, the power to understand reality. And this knowledge is perhaps more valuable than going faster than light, because knowledge gives you power. Understanding gives you power. And the universe, no matter how large and mysterious, is understandable. Mathematics, physics, logic. The speed of light limit reminds you, the universe isn't limitless, but it's as large as you can understand. And that, perhaps, is the deepest bedrock truth.